Hi, everyone. Welcome to Lattice Thought Leadership Panel. Today's topic is new space system requirements. My name is Jim Tavacoli. I'm the head of aerospace and business at Lattice Semiconductor. This past July, pictures were released from the James Webb Space Telescope showing a giant leap forward in knowledge of what exists beyond what we previously could see. Leaping forward requires innovation and efficiency in exploration of space. As new space applications are emerging, the industry is in need of efficient solutions with scale for the whole constellation on orbits ranging from LEO to GEO and beyond. In these LinkedIn live sessions, we want to focus on innovative, market leading topics that require our community of partners and ecosystem stakeholders to share their insights on how they're creating new innovative space systems. I look forward to the discussion with our panel members on what's happening in the space market and how we can help our community in bringing some of our leading edge FPGA technologies to the market. Gianluca, please go ahead and introduce yourself.
Hi everyone, I'm Gianluca Furano. I work in the ESA European Space Technology Center Data System Division since 2003. I'm responsible for R&D in the area of new data system, especially for what concerns use of artificial intelligence in space.
Great to have you. Alberto, please introduce yourself.
Hello, everyone. My name is Alberto Moreno. I work at the EEE Parts Engineering and Radiation team at Tesat-Spacecom, or just Tesat. Tesat is an independently operating German subsidiary of Airbus Defence and Space that develops, produces, and tests communication payloads like power amplifiers, laser communication terminals, and many more. I also support the DLR, the German Aerospace Agency, as a technical advisor for semiconductor devices with focus on integrated circuits.
Thank you for joining us. And David, please introduce yourself.
Good day, everyone. My name is David Miyujas. I'm the Senior Director for Standard Products within CAES Space Systems Division. I'm responsible for the portfolio of radiation-hardened and radiation-tolerant microelectronics spanning memory, interconnect logic, microprocessors, clocks, and most recently FPGA through our partnership with Lattice.
Thanks for joining us. I'm really excited to discuss challenges and opportunities around implementing next generation space systems. Before we dive into the application requirements, let's talk a moment about what new space is. Gianluca, could you provide some insights into your thinking of new space and their application requirements from your experience?
My experience comes from an agency that lives out of large institutional mission that in a certain sense are the opposite of new space. But what we have learned in the past few years that the two things, rather than being in opposition, are kind of helping each other. As we see it here, new space is a kind of the foam over the beer. It is produced fast, it goes away fast, but is where the real innovation then subsides into the established space occurs. And as European Space Agency, we are more and more investing resources and money into what are exciting and more daring mission what we do in the established space.
That's really well said. So, Alberto, can you talk about some of the challenges from your vantage point and some of the requirements that you see?
Yeah, so we are already working, developing, producing new space products. We do not see a homogeneous landscape for new space. It's catchy name for many requirements that depend on the customer. We see some commonalities. Some of them are, for example, automotive parts are normally accepted without any further quality tests like screening or qualification. We see, you need to test radiation tests normally, because unless you use LEO products, you don't have any data in that regard. And we are, to guarantee the reliability, we are still using derating and layout rules from traditional space. So we want the reliability, even using other parts that have not traditionally been high reliability.
Thank you. And David, can you talk about the trends you see and some of the problems um, you see customers trying to solve?
Yeah, absolutely. I mean, space is all a buzz nowadays, and the industry is growing significantly. None of that more than in the new space segment. And the reason for that is historically, if you had a single large satellite operating in very high altitude or GEO, that served a specific function. What we're looking at today in new space is we're basically breaking up that very large satellite that had a 15-year mission duration and disaggregating that into dozens or hundreds or thousands of different satellites at a much lower orbit. And so with that comes a significant amount of growth, significant amount of challenges. You need to ensure that you have the bleeding edge technology that is able to survive in that environment, even if LEO environments are a little less harsh than the GEO or deep space type missions. There are still factors like radiation and reliability that are critical. And as Alberto stated, every customer seems to have his or her own set of unique requirements. And so you really need to tailor the component design, the component qualification, and the system in support of all those requirements.
That's really well said. So what I'm hearing is that there are a wide variety of requirements in a market that's moving fast. The challenge is really how to leverage new technologies in an industry that has traditionally used mature microelectronics. I think viewers will be interested in hearing how to meet these requirements and still deliver a level of functionality and performance, above what has been achieved in the past in traditional systems. Um, these systems and the development of these systems have been sort of forced to choose older hardware components with limited flexibility that were really challenging to scale. And with new space systems, the industry is looking for products that address new application requirements and have the ability to scale efficiently. David, in your view, what are some of the key factors to consider when designing for a new space system?
I touched upon them a little earlier, but really, from my perspective, radiation, right? Regardless where you operate, LEO, MEO, GEO, deep space, you're going to have radiation as a factor. So you need to make sure that you don't have latch up, that you can survive the duration of the mission. So all that radiation that gets assigned onto the components in the system needs to continue to function. The satellite needs to continue to execute its mission for the duration that it was intended for. So radiation is a big part of it. And the fact that we're leveraging bleeding edge technology in new space, not all bleeding edge technology is able to perform in that new space environment or has that inherent radiation tolerance. The FPGA, as an example, very robust, has that inherent radiation tolerance and is able to execute missions of that type. So very important criteria selection and upscreening to guarantee that those types of components are able to survive that environment. Beyond that, you're also looking at the reliability of the part. Much like your vehicle, you expect to drive it in hot, cold temperatures. You expect to have it for many, many years without having to go in for maintenance. And so satellites, very similar. You need to make sure that your components don't fail, that your system doesn't fail, as it's a little harder to maintain the satellite when it's in orbit, unlike your vehicle.
And David, if we can rephrase what you just said, new space is a lot commercially driven. You have a customer that has very specific requirement, and among those requirements, there are reliability, as you just said, but also availability. Most of the impact of radiation on parts like complex digital parts like FPGA are temporary outages that when you sell a service that needs to, for example, take photo at a very precise specific time or a very precise location, need to guarantee that your system has to work at that time. And the correct management of this normally is the biggest hurdle in many new space systems. A lot of new space companies are very good in producing the first demo mission without specific requirement, and they start to fall apart when they have to really deliver a commercial service. So with strings attached like availability.
Well said, Gianluca. Thank you.
And just to build on that, Alberto, I think the viewers will be interested in hearing about, how do you guys, scale to meet the wide variety of requirements in your system architecture and development?
So as we mentioned before, we are seeing much faster developments in new space and cutting edge technologies reaching those products much faster than what we were seeing with traditional space, and that is interesting because we can get heritage on those platforms and then scale them to class one. So what we are trying to do is to have a single platform from new space to class one and use the new space product kind of as a demonstrator, but a demonstrator that works in orbit. So we do not need to, so we test everything before we launch. And well, some details about how we use the same platform from new space to class one. So we passive components are normally easy to replace because they have the same footprint. But critical components like FPGAs or microcontrollers, they need an ecosystem and they are more difficult to replace. So we are trying to use the same main components in those areas. And there are movements from the industry and the space agencies in that direction to accept plastic components. There are several specifications under development.
Thank you for sharing that. And Gianluca, let's talk a little bit about the different level of criticality within the same system. And how do you streamline the development and deployment of such systems?
I was just about to react on that, to what Alberto just said. The way in we see between new space and established systems is to manage, especially from our end customer point of view, the system a more granular way. In the past, everything was class one, regardless of their function. Now we are ready, and in this sense, we are already issuing several specifications to accept systems that are more heterogeneous, where depending on the function, the criticality of the function, different classes of components can be accepted. There are already some European ECSS standard guidebooks on that, and we're moving, I think, fast forward in the sense to, from one side, ease the economy of part procurement in some of these functions. From a side, also to accept more advanced functions that are made available by use of more modern and more cutting-edge electronic components, especially in the area of highly integrated digital electronics.
And so, what I'm hearing here is you're adopting architectures and design methodologies that want to rely on advanced microelectronics to scale and meet a wide variety of requirements, of course, with reliability in mind. Now, I want to ask you to talk about how the ecosystem is evolving to meet these challenging requirements. Can you talk a little bit more about that?
The ecosystem is a huge challenge in general, because especially in Europe, where we see beside the large scale integrator, a very fragmented know-how landscape. So you cannot rely on the same level of know-how on many companies. It's important to rely not only on known good parts, so known good reference designs, on tools that allow a very quick learning curve for newcomers in the arena. So what you mean with ecosystem touches really end to end the whole product life cycle, from the design, the contractualization, the production. There are very few companies in Europe that are able to do that. These are only basically the large scale integrators and their close ecosystem. But we as European Space have to work with everybody, and we welcome the possibility to use any part that has a strong commercial heritage, because this means that the actual number of potential users and know-how, distributed know-how of the part, it's much more diffuse.
Thank you for sharing. And I think standards will help accelerate deployment. Alberto, in your experience, what standards are in place and what's needed to accelerate deployment of these new systems?
In my opinion, the market is moving much faster than the standards. We are normally working with our internal new space specifications because we don't see system standards for new space from agencies like NASA and ESA, not so far. We're seeing some movements in the direction. So, for example, on the component level, the mill system is working on plastic level, and ESA is working on the ESCC 9000P that will have a different number once it's released, but that should become available beginning of next year. And those will allow plastic components to be used up to class 1, which will simplify that approach of having one platform for all levels. But there is much more to be done on the system level.
No, I tend to agree with David. Standards are a kind of collection of the know-how we have so far, but in this specific sector of the market, we are moving so fast that some of the standards have difficulty in catching up. And specifically for plastic component, this is my anecdotal observation. Systems built exclusively with automatic pick and place, so inheriting what is normal in many commercial process, industrial electronic processes, or even commercial electronic processes, tend to be much more reliable or suffering less problems than the old one, especially using a lot of ceramic hand-mounted components. So this is anecdotal. We are observing this, and this level of know-how needs to be picked by future industrial standards for sure.
Yeah, we're really seeing through the customer base. For each customer, for each mission, you're seeing a unique set of requirements, right? Because when you're talking about space, you're really looking at a spectrum of quality, of assurance, of reliability. And on the low end, you can simply leverage automotive parts. On the high end, you leverage class 1 parts. But then there's so many permutation iterations for what is truly important for that customer, for that mission. It's really mixing and matching between that spectrum to apply to that specific component or system and have a successful program.
And David, can you talk about standards, not just for components, but also for assembly and integration?
Yeah, absolutely. I'll start off with the components, and I think Alberto's got a lot of insight as it relates to the assembly. Um, for the components, we mentioned multiple standards. We mentioned ESA standards. We mentioned NASA PEM standards. Really, QML standards that have historically supported Class 1 missions through the DLA organization, Defense Logistics Agency. That was kind of the gold standard for GEO missions. If you didn't have that seal of approval, that stamp, you really couldn't use it on those types of missions or deep space missions. Now, obviously, those third-party entities that oversee the quality and the reliability of the manufacturers that make these components, they're also adapting, right? Albeit not as quickly as the market is moving. The industry is working with DLA to define what does a plastic component QML device look like. So there is continuous efforts, organic class Y. We are working to get a standard in order to support some of the higher end new space missions. But going back to my prior statement, for every customer, for every mission in new space, we seem to have a unique subset of requirements that are applied for that mission.
Mm-hmm. And Alberto, how do you see the component types that you're looking at, such as FPGAs or other components, um, helping you with kind of adopting or evolving with the standards, and the multiple level of assurance and reliability requirements?
So, well, regarding what David said about assembly, we are using the traditional space assembly specifications, the same layout rules and so on. And about FPGAs in particular, as I said before, they are tantamount for the mission. They are the heart of the mission and the brain, and we don't want to change them between platforms. So we don't have to change the software, the ecosystem, and so on. We see that there are many fields in which FPGAs are going to play a pivotal role for new space, and in particular small FPGAs, because in space we always need redundancy of some kind. Even if you have a rad-hard part, say microcontroller or an FPGA, if you need to reprogram it or change the code on it, you need some FPGA to do that. So, and also as a watchdog. So even for other applications than what you see on Earth, small FPGAs are very interesting.
There is no doubt there is need for flexibility, particularly to scale to meet the new space application requirements and enable faster deployment. We recognize that space systems require FPGAs of all sizes. As an FPGA company, we're focused on small to medium density FPGAs, and this is where Lattice can really help with architecture of these new systems. We believe our inherent radiation resilient FPGAs that are architected to deliver really low power in small footprints are a good fit. And we think they're optimized to support new space architectures and especially distributed system requirements. David, interested in your perspectives on this and how you see these components and their radiation resilience meeting the system requirements.
Yeah, great question, Jim. It's really been, in my opinion, an underserved market. There's always been, legacy class 1 FPGAs that have, draw more power, that have less logical density, and then you have, the very large behemoth FPGAs on the upper right. So really, there's kind of been a bit of an underserved element that we think for distributed processing edge processing, we really have an interesting solution here that enables something that wasn't available before. The inherent radiation tolerance, CAES takes that product, tests it, ensures that that the radiation performance is as intended, and we're able to guarantee that behind the product. Effectively, when you're looking at the spectrum of space missions, what Gianluca and Alberto were referencing was the fact that if you start off with a new space mission that has X amount of years required for it, the FPGA that we can leverage, the ecosystem around it, the software that goes around it, it is a significant amount of effort for the teams to get that up and running. And so if your mission assurance requirements scale, depending on the customer, depending on the profile that you're looking to reuse that same architecture, you don't want to swap out a different FPGA, because that, requalification, the entire software ecosystem needs to change. It's a significant amount of burden. So I think when we have a very swap efficient solution that has the radiation performance, and that we're able to scale the reliability and the mission assurance with the mission, I think that's a significant differentiator, and something that the market is in dire need of.
Not only, David, if you add to that the agility that use of distributed FPGAs gives into a system. So basically, this allows to decouple a lot of the hardware development versus the mixed software and FPGA code development, and helps in meeting what are normally really hard deadlines that you have when developing a new space systems. And they use a known one-time programmable FPGA. In this sense, it's a key factor when your distributed system not as ready as it should be on your first day on the test table.
Thank you for that, Gianluca. Any additional thoughts, Alberto?
Yeah, I wanted to build up on what Gianluca just said. We are seeing in new space more tolerance to that tweaks approach. So to be able to reprogram in orbit. And that's a very important thing, because you can improve your system when it is launched. It's not so unflexible as it was in traditional space. And for that, is where we need this, for this flexibility, we need that redundancy that uses small FPGAs and distributed system that doesn't have to change the whole system with one reprogramming.
Very well said. A key element of space market enablement is the ecosystem collaboration. This is a fast-moving market with evolving set of requirements, and no one entity has all the solutions. We've created a strong partnership with CAES to enable solutions that scale in terms of reliability and assurance level in order to meet different mission types and the requirements. In addition, we've also established a forum through which radiation test data collected by us and other ecosystem members, as well as the hardware and software that goes along with it, are shared out openly to enable the ecosystem. To just wrap up, I want to thank the panel members for the insights. And, if you want to learn more, feel free to visit our website as well as CAES website. And to stay up to date with the latest news, be sure to follow us on LinkedIn, Facebook, Twitter, what have you. Again, thanks again, everyone, for your time.
Thank you.
Thank you, Jim.
Thank you, everyone.